Hi everyone. This is a video presentation of a paper Huge, an efficient and scalable subgraph enumeration system. I am Zhenyi Yang from the University of New South Wales. This paper is a joint work with Longbin Lai from the Alibaba Group and Xueming Lin, Kongjang Hao, Wenjie Zhang from the University of New South Wales. Here is the outline of this presentation. Firstly, I will introduce the problem definition and briefly go through existing works. Then I will talk about the proposed Huge system, including its three main contributions. After that, experimental evaluation will be presented. Finally, I will conclude the paper and discuss some potential extensions of Huge system. This paper studies the problem of subgraph enumeration. Specifically, given a query graph Q and a data graph G, the problem of subgraph enumeration is to find all subgraph instances in G that are isomorphic to a query graph Q. Such subgraphs are called matches. Here in this given example below, we can find three matches of the query graph in the given data graph. Here is the first one, the second one, and the third one. As subgraph enumeration is one of the most fundamental problems in graph analysis, and the graph size is increasing very rapidly nowadays. Many distributed algorithms of subgraph enumeration have been proposed. We classify them into primarily two types. The first type is join-based algorithms. Join-based algorithms use distributed join to compute matches. The main differences among them are the join algorithms they use and the join order they adopt. Since the data graph is partitioned among the cluster, join-based algorithms push the intermediate results from the host machine to remote machines to execute a distributed join. Such shuffling can result in high tension in both communication and memory usage due to the exponentially increasing number of intermediate results in subgraph enumeration. To reduce the volume of communication, pool-based algorithms are developed in recent years. Instead of pushing intermediate results, they pull the data graph from the remote machines to the host and cache remote vertices for future use. However, directly adopting pool-based communication may not lead to a reduction in computation and communication time, as we will discuss in the following slides. We conducted an initial experiment on 4 representative state-of-the-art algorithms. We use a simple square query as shown here. And for data graph, we use the popular benchmark graph, LiveJournal. We select 2 join-based algorithms, seed and big join, and 2 pool-based algorithms, Bennu and Reds. Seed utilizes binary join algorithm with optimal Bushy plan. Big join utilizes distributed worst-case optimal join algorithm. To achieve pool-based communication, Bennu stores the data graph entirely in an external distributed key-value database and send pull requests directly to the external database. By doing so, each machine can compute the matches using traditional backtracking algorithm as in a single machine. Reds is another pool-based algorithm. It implements its own compute engine without external dependencies. Observe that the matches of a star rooted at a vertex can be enumerated from its neighbors. Reds expand the matches by a star in each round by pulling remote vertices and compute the stars locally. It then verifies the edges between stars using edge verification requests to filter out false positives. Here is the results of the initial experiments. As expected, 2 join-based algorithms, seed and big join, show high communication volume and memory consumption, especially for the binary join algorithm, seed. Pool-based algorithm, Bennu and Reds, achieve less communication volume, and Bennu has the least communication volume of about 25 gigabytes. However, neither Bennu nor Reds demonstrate an improved computation or communication time compared to join-based algorithms. For Bennu, it is mainly because the large overhead of using external database. Moreover, the traditional backtracking algorithm employed in Bennu uses depth-first search, DFS, which can result in low network and CPU utilization. For Reds, as the star-based execution plan has already been shown in existing works to be suboptimal, a large number of intermediate results are generated during computation and significantly harm the performance. As we know that the efficiency and scalability of distributed subgraph enumeration are jointly determined by computation, communication, and memory management, but none of the existing works achieve satisfactory performance for all three perspectives. Therefore, we developed Huge. As shown in this table, Huge renders the smallest computation and communication time, as well as communication volume, with the peak memory consumption only slightly larger than Bennu. We identify three impact factors that jointly affect the overall performance of distributed subgraph enumeration. The first one is execution plan. Execution plan plays an important role in distributed subgraph enumeration. However, previous works achieve optimality only in a rather specific context, subject to the pre-configured join algorithm and communication mode. For example, seed is optimal among the hash-based distributed binary join algorithm, and the optimal plan of rats is computed specifically for its pooling-based design. As a result, none of them can guarantee the best performance by all means. The second factor is communication mode. While pooling communication can potentially reduce communication volume, it is non-trivial to make it eventually improve overall performance. More importantly, an efficient plan may require both pushing and pooling. The third factor is scheduling strategy. Although DFS strategy has small memory requirements, it can suffer from low network and CPU utilization. To increase hardware utilization, breadth first search (BFS) strategy are more widely used. However, it demands a large number of memory to maintain the intermediate results. Static heuristics such as batching or region group are used to limit the number of firstly matched vertex or edge. Those techniques can ease memory tension, but lacking a tight bound and can sometimes perform poorly in practice. We take on all challenges mentioned above by presenting the system Huge, short for push-and-pulling hybrid subgraph enumeration system. Specifically, Huge features an advanced execution plan that generates an optimal plan in a more generic context, not restricting to a fixed join algorithm or communication mode. Secondly, it also features a push-and-pulling hybrid compute engine that can efficiently support both push-in-based and pull-based communication. It also has a DFS/BFS adaptive scheduler to achieve memory-bounded execution without sacrificing computing efficiency. In the following slides, I will discuss each contribution one by one. For execution plan, we break down an execution into logic and physical aspects. Logically speaking, the task of subgraph enumeration can be represented in a unified join-based framework, where the matches are computed by a series of joins of its subgraphs. Such subgraphs are called join units. Common join units are edges, stars, and clicks. As using clicks as the join units requires index, and Huge does not rely on any index, we only allowed edges and stars as join units in Huge system. The join is processed under certain join order. Typical join order follows left deep tree or bushy tree. Huge adopts the bushy tree by default. In the physical aspect, for each join, Huge decides the best join algorithm and communication mode to actually perform the join according to the cost function. For join algorithm, Huge can select from traditional distributed hash join and also worst-case optimal join. With respect to communication mode, Huge is not restricted to a single communication mode, that both pushing and pulling are supported. By breaking down the execution plans into two parts, we implemented a dynamic programming-based optimizer that takes both computation and communication into consideration to minimize the overall execution time. Here are two example plans generated by Huge's optimizer. The left one is the plan for a four-click, as illustrated. All two joins in this plan are executed using worst-case optimal join algorithms with supporting communication mode. The second one is the plan for a five-pass. We see a mix of worst-case optimal join with polling for the first join and hash join with pushing for the second join. This refers to as hybrid plans, as in the single machine setting. However, it is apparently more challenging to design and implement this in a distributed context, given that there exists different communication modes. We show in our paper that our unified join framework can represent the plans of all existing works. Therefore, the execution plan of existing works can be readily plugged in to the system to enjoy automatic performance improvement by Huge. After getting an execution plan, the plan is executed by Huge's compute engine model. Huge adopts the popular data flow model for distributed execution. The execution plan are translated into a data flow graph using different Huge operators. More details can be found in the paper. In addition, as an optimal plan may require both pushing and polling communication mode, the compute engine in Huge supports dual communication mode. In particular, we find that cache is a key to the efficient polling-based communication. So we designed a new cache policy with two-stage execution strategy. This makes polling-based communication more efficient. Finally, the compute engine employs a two-layer intra and inter-machine dynamic work stealing mechanism for better load balancing. This graph shows the system architecture of Huge. Huge adopts the shared nothing architecture in the cluster. Each machine runs an RPC server and the RPC client to serve polling requests. The server supports two RPCs, getting neighbors and still work. Getting neighbors takes a list of vertices and returns their neighbors. Still work can steal unprocessed tasks and send them to other machines for load balancing. The router pushes data to remote machine using TCP connections to handle pushing-based communications. In addition, Huge initializes a number of workers upon starting to run the de facto computation. Each machine has access to the local partition of the data graph, the RPC client, and the in-memory cache. If requesting a local vertex, it will return the neighbors from the local partition. Otherwise, it either returns the cached value, if any, or send RPC requests to obtain the neighbors and caches them. Finally, each machine owns a scheduler to achieve bounded memory execution. I will then introduce the ideas of our cache design and the scheduler in the following slides. As mentioned, we noticed that an efficient cache structure is a key to high-performance polling-based communication, which reduces polling requests on network. Existing pool-based algorithms, such as Banyu, directly use traditional cache structure, such as a concurrent LRU cache shared by all workers. We identify two vital issues of doing so. The first one is memory copies. Getting a vertex from the cache involves at least locating the vertex, updating cache position, and copying the vertex out. So memory copies is inevitable to avoid because of the dangling pointers it may cause in traditional cache policy. Secondly, since the shared cache will be concurrently written and read by multiple workers, lock must be imposed on the cache to avoid inconsistencies caused by data racing. While there are many techniques on reducing lock contentions, they are not completely lock-free. We target at a completely zero copy and lock-free cache access in Huge. To achieve that, we designed a two-stage execution strategy. In the fetch stage, the compute engine aggregates remote vertices, sends pull requests in bulk, and writes remote vertices to the cache. Since cache writing can be overlapped with the asynchronous RPC requests, we use only one writer to write cache, which is log-free. In the actual computation stage, the intersection stage, the compute engine reads the cache and compute candidates by using intersections. Since the intersection stage is read-only, multiple workers can access the cache without any locks or memory copies. Note that such design requires synchronization between fetch stage and intersect stage. However, we show in our experiment that the synchronization cost is small with a value less than 7.5%, while achieving massive performance improvements on polling. In addition, the aggregation of RPC requests can improve network utilizations. Please refer to our paper for more details. Furthermore, Huge features a DFS/BFS adaptive scheduler. Each operator is equipped with a fixed size output queue. The scheduler will dynamically monitor the output queue. It adopts BFS-style scheduling whenever possible to fully leverage parallelism. To fully leverage the degree of parallelism and switch adaptively to DFS-style scheduling when the output queue of the current running operator is full. In this way, we can bound memory usage under a tight bound. Then I will present experimental evaluation. The experiments are conducted on 2 clusters, one local cluster with 10 machines and one AWS cluster with 16 AWS instances. We use the AWS cluster for the web-scale data graph only. For datasets, we use 7 real-world data graphs and 8 queries selected from parallel walks. The cache size used in polling-based communication are 30% of the data graph. We allowed 3-hour maximum running time for each query, and the queries that cannot finish within 3 hours are marked overtime. Here are the details of the data and query graphs. The largest data graph, CurlWeb20, has more than 42 billion edges. We only use it in the web-scale experiment. Firstly, let's see how Huge can speed up the logic plan of existing works using the data graph live journal. Here, we run the execution plans of Bennu, Reds, Seed, and Big Join in Huge system and compare the results with the original algorithms. From the figure, we can see that Huge speed up the existing plans by up to 49 times in Q1 and Q2. And thanks to its bounded memory execution, when Seed runs out of memory on Q1, Huge successfully completes the query by using the same logic plan. Next, let's see the all-around comparisons. Huge is able to outperform other algorithms in almost all cases. Finally, we evaluate the scalability of Huge by varying the number of machines in the cluster. As we can see, Huge achieves almost linear scalability. Moreover, we test the ability of handling web-scale graph using the data graph CurlWeb on the AWS cluster. Since the number of matches are estimated to be dramatically large, we run the algorithm for 1 hour and calculate the average throughput. Huge is the only system that completes this experiment thanks to its newly designed execution plan, compute engine, and scheduler. In conclusion, this paper presents an efficient and scalable subgraph enumeration system, Huge. Huge is also designed to be flexible for extending more functionalities. We also discussed in the paper of its potentials to be extended to cipher-based distributed graph databases, graph mining systems, and systems for solving traditional shortest path problem or hope-constrained path problems. This is the end of this presentation. Thank you for listening.